of long tutorial and will be given by all of us. All of us comes from Sapienza, University of Rome. This logo, as Sharon pointed out, is very similar to Starbucks, but officially belongs to Sapienza from more than 700 years. It was renovated, by the way, recently.
You can trust them.
Yeah, yeah, in fact, it is easily. But you know, US, they didn't know that in Italy we had the universities still before they were invented. So I'm joking, of course. So just many slides will be freely available on the web, and it's important, I have to say, that in Italy, as you know, we have, after the COVID, the recovery plan, and the part of this work is part of the basic research that we are conducting in the context of a big project about Industry 4.0 that will finance us for the next 4 years, basically. So hopefully we'll come back also next year with the stuff that we will have.
I take it as commitment.
Absolutely, yes. So who we are, because many of you maybe doesn't know us, there is Francesco, that is quite an associate professor, he will begin next year, and he works a lot in ambient intelligence and have a lot of experience in real industrial projects. We have, for example, on the table sensors that Francesco with the other built from the firmware on, in order to have some industrial project in which we are really deployed into real factories. There is me that probably you know a little bit more, that I am currently leading the group in BPM, so processes, services and software management at the Sapienza University of Rome. At the end of the tutorial I will speak a little bit, because in 2 weeks there is the deadline for SummerSOC 2023 in Rome, that I hope to see many of you there, because that will be the 3rd decade of SummerSOC, that somehow is the sister conference of this one, so I would like really to host you in Rome. But we'll have a dedicated session afterwards. And then there are Flavia, that is a PhD student with us, also in Industry 4.0, and Luciana, that is another PhD student of us, dealing more on the aspect of formal methods. So what we'll talk about, we'll give an introduction to smart manufacturing, or at least what is smart manufacturing for us. Then we'll deal a little bit with modeling Industry 4.0 system as a composition of services. Some of you remember that 20 years ago, at the first SummerSOC, me and Giuseppe De Giallo, that is not here, presented what is famous called as the Roman model. So basically we can say that we present a little bit how the Roman model moves to the new decade with some nice industrial aspect. We will deal a little bit with complexity that we have. We'll show many automated reasoning approach on services, moving from planning to usage of stochastic systems like LMDP, that will be markup decision processes. And then we present the tools that we have currently used for large experiments and for real application, and there will be a live demo of it, and of course this will be public available on the web for according to open science principle, and then there will be a little bit of philosophical consideration at the end. So I give now the floor to Francesco for the introduction to smart manufacturing. Please interrupt us whenever you like. Let's try to have a very lively discussion.
So good morning. We start with a brief introduction to smart manufacturing. Now, the title of this slide is Smart Manufacturing Industry 4.0. These two terms are actually not the same. Many times they are interchanged one each other. Actually, smart manufacturing is much more orthogonal term that basically could be applied also to Industry 3.0 to Industry 3.0. What is Industry 4.0 is basically the last evolution of industry. Now we also talk about Industry 5.0, which also integrates human-robot interaction aspects. But basically, now we are still in the period where we are actually trying to really apply Industry 4.0. So, what is smart manufacturing? It's a concept that is actually functional to increase the productivity and quality of the products, to ease the worker's life, and to define new business opportunities. And in this context, digital factory is a key concept, because the idea behind smart manufacturing is that actually we use data coming from factories and also from supply chains, which is one of the concepts we will try to enforce during this presentation. What is manufacturing smartness is basically an optimized use of resources, and basically the idea is to increase the intelligence of machinery and production lines, but also manufacturing chains, decreasing the need for human intervention. Now we will see some of the emerging trends in smart manufacturing. First of all, the first trend, factories and machines are increasingly complex. Previously, machines were mainly mechanical stuff. Now they all have digital interfaces that can be queried. They can be driven and manipulated from outside, from information systems. Mass customization, this is a kind of midway between mass production and customized production. The idea behind mass customization is that I have mass production, but in this mass production I have some degree of freedom in customizing the services. For example, I can have a factory that produces boxes of chocolates, which can be done, of course, in mass production, and I decide to customize the boxes with the kind of chocolates that I have inside the boxes. This is basically a simple example of mass customization. Also, this is very important, business processes are not considered isolated. If we really want to have smart manufacturing, basically the idea is that the different business processes of the different companies that are involved in a supply chain basically must communicate to each other.
So you have choreographies in mind?
Yes, exactly. Yes. Zero defect manufacturing. This is another emerging trend. The idea is that we use data in order to obtain manufacturing processes which is designed to be zero defect. What does it mean to be zero defect? Of course, not really zero defect at all. It's the number of products that comes out from my factory are usually without any defect. So any defect that appears, it must come from a wrong employment of the product that I have created. And this involves, of course, following the product during the different phases of the life cycle. And of course involves the introduction of prediction system and detecting defects. This is also connected to the concept of digital twin. We will not explicitly talk about digital twins during this talk, but the idea is that digital twins are always there to provide information. Basically, all the system that we are going to present is based on information that can be extracted by using digital twins. But here in this talk, digital twins are only tools to obtain output. Smart products. The idea behind smart products is basically that a product must be followed during all the different phases of the life of the product, from the design, but also to the employment, and also to the part of the life of the product, which is called demanufacturing or remanufacturing, which is part of the concept of circular economy. The idea behind smart products is that basically we have these products that can be followed during their life. They can receive firmware updates, they have predictive capacity, they have predictive maintenance capacity, for example. And one interesting thing is that in smart manufacturing, a smart product may be a machinery for another company. So what happens is that you have a smart product. So as a company that produces machinery, you are following your product as it is your product. But for another company, your product is basically part of its manufacturing chain. So it becomes a machinery for that. Concept of manufacturing network is always connected to the concept of supply chain. What is a manufacturing network? Basically, it's a kind of coalition between different companies that have that join their efforts in order to produce a specific product. And the idea and what we are going to present during the demo today, but also during the talk we will have this afternoon, is that basically all of this network must be agile and adaptive. Now, this is a slide that is taken by a talk from Professor Papazoglou, where we have the barriers for smart manufacturing. Here we will focus mainly on two of the barriers. One barrier is that the challenge in smart manufacturing is that you need to track and trace product from the cradle to the grave. So in all the phases of the product. But here the problem that you have is that basically you must be able to integrate data, you must be able to abstract your data and your services. So another key challenge is that at this point there is a limited point-to-point connection between business IT and factory automation. There is this connection between the enterprise level and the shop floor. What does it mean is that basically you treat your company, the schedule of your company, in a separate way from the manufacturing line. So 7 steps to obtain smart manufacturing network. Reference architecture, we will talk about one of the proposed reference architecture. Connectivity, of course, between the enterprise and plant floor system, but this is a part of Industry 4.0, so this is something, let's say, that is in some way already achieved. Then raising the level of manufacturing abstraction. This will be the main topic that basically we will face in this tutorial. Massimo will tell more about this later. Then once you are able to raise the level of manufacturing abstraction, at that point you can add smartness and analytics to your factory or to your supply chain, and you can proceed with the other step of to obtain real smart manufacturing networks. Smart manufacturing actors. This is very important because from the point of view of smart manufacturing, the kind of actors that are involved are many and very different. Let's start from humans. Humans are also actors in smart manufacturing because they are going to collaborate with robots, for example. And there are different kinds of humans that are involved in smart manufacturing. You have manufacturing line operators, line supervisors, manager, of course the software development teams, product designer, process designer. You have a lot of different humans that are involved in order to obtain smart manufacturing. Of course, machines. Here for machines we have both new machines that are, let's say, Industry 4.0 or Industry 5.0 native, but also updated and extended ones. This is something, for example, we are a lot involved in Italy. Our activity is often about taking an old machinery and basically wrapping this machinery in terms of services. Organizations, because in some cases you cannot have really a deep understanding of what happened in a specific organization, so you treat an entire organization as a service instead of focusing on the single components of the organization. Of course, information systems, which are, the basic components of smart manufacturing, and smart products. Of course, information systems, there are traditional information systems such as ERP, but also more modern category of information systems in smart manufacturing, such as manufacturing execution systems. So, we talked about reference architecture. Now, the most famous reference architecture in Industry 4.0 is the RAMI specification, which was a German initiative that then was adopted at the European level. This is a three-dimensional, let's say, architecture where you have on one axis the life cycle, you have for the type of product, you have the development and the maintenance of the product. For the instance, that is the specific product you are producing, you have basically the production and the maintenance, but intended on the specific item. On the other axis, you basically have the scale you are considering your smart manufacturing, starting from the product, going to the field device, arriving to the connected world and to your manufacturing network. Now we'll focus a little bit more on the vertical axis, where we have the logical layers in Rami. These layers are the asset layer, where we have the physical components. We have the integration layer, where information is transformed and processed in order to be useful for processing. We have the communication layer, where all the standards for communication are, for example, MQTT. We have the information layer, where basically the data is turned into useful information, and here this layer, in some cases, it is referred to the context extraction layer, and digital twins basically belong to this layer. Then we have the functional layer, where we formally describe functions, and the business layer, where all of these functions are basically integrated into process models. So we move to Industry 4.0 supply chain, and the concept of agility. What is agility for Industry 4.0 supply chain is a mix of responsiveness and adaptivity. Basically, responsiveness is the ability to react to the disruption along the supply chain. Such a kind of disruption could be, for example, a machinery that got broken, but also an organization that is not anymore available for the supply chain, also for socio-political reasons. I mean, a war explodes, and basically you cannot buy more components from one single organization, and this provokes, let's say, a chain of organizations that you cannot access anymore. Adaptivity instead is something more complex to achieve. We will mainly talk about responsiveness in this talk, but we will also consider a little bit of adaptivity. The adaptivity is the ability to adapt to change in the market while remaining competitive. What does it mean? It means that basically I can forecast what is going to happen to the market, but also what is going to happen to machines, and I decide to change automatically my supply chain. And here in adaptivity, we can also find business opportunities. And responsiveness is part of what is generally called resilience. So, let's see how supply chains are located with respect to the logical layers of Rami. Basically, we have, of course, the services. During this tutorial, we will see how we can model all of the participants of the supply chain, or the machineries inside the factory, using services, which stand at the functional level, as we said before. And agile processes, of course, are at the business level of the Rami architecture. So the idea is that basically, from the point of view of what we are going to present today, what happens at the information, communication, integration, and asset layer is something that is given for granted. So we are only working at the functional, at the business level. So the idea is that what we want to do in this tutorial is to show how artificial intelligence can be used for supply chain adaptivity and responsiveness. The idea is that we have a set of services that can basically that have common interfaces and can and can basically execute steps of our supply chain, and we combine them dynamically by looking at how the conditions of the single machinery changes and evolves over time. We also modeled geopolitical issues, and the idea also is that all of these supply chain adaptivity should also be considered in light of one phenomenon, which is modern machine leasing. What is machine leasing is basically a new kind of services where machines are actually borrowed, let's say, from specific organizations, so they can be dynamically bought and employed in the supply chain. So now I leave the floor to Massimo.
Okay. So this introduction was aiming, of course, many of you, especially those who are coming from Germany, already knows the concept of ramming, because ramming was basically starting from a German initiative. But we believe that it was useful to have a common background, especially for the students. We are in a school at the end, to have a common background of what are the basic pillars if you want to address Industry 4.0 stuff, what are the must-know points that are fundamental to address. And we try to give some insight where, in my opinion, the service community can give contribution. So the idea is that I have these big systems, they are industrial systems, many often they are inside factories. For example, if you want to enter in the factories, you have to wear your specific shoes, otherwise they cannot make you touch for safety reasons the machines. How can we see these machines as services? And this is what we would like. So the abstraction that we are supposing is that whatever can be a service. So all the actors that Francesco mentioned before can be represented as services. Also the human is a service. Because in the end, in the machines, in the factory settings, the humans have two ways to interact with the environment. Or it will be equipped with some wearable device, maybe a touch screen on the station or whatever. In any case, the interface of this man can be seen as a service, or it will be interacting with the normal workstation. Maybe this is in the back office. Again, it can be seen as a service. I call a kind of two-way services. On one side you have the software interface, on the other side there is the human. For me it's the same as if I have a service that writes in a database. In that case, the service, in one case the service writes in the database, in the other case the service sends us a pop-up or whatever you like to a human, he does the task, and the task will be sent back to the services.
Which is nothing new, like Amazon Mechanical Turk.
Yes, in fact, but in a production environment, this is how the humans work. They can have autonomy, but in any case, the autonomy, especially for safety reasons, should be somehow controlled, should be orchestrated, let me use the terms that we like. Of course, now in the fabric we have a lot of robots, and I think that all of us agree that the robots can be seen as a service, because at the end, there is a software layer that can drive the robots. The machine itself as robot. So the idea is that each of them what does? It performs actions and changes state, and is ready to execute the next actions among those ones that are provided at that steps of the computation. Because in the production process, everything is well defined. Optionally, I will see optionally because we present a different level of modeling, the machines, the service, sorry, may fail during an action, and it may fail with a given probability. We will see that here's machine learning will enter. Because here you can have, for example, digital twins that will allow the service to make prediction when it may fail. So the probability that for now we can say are constant can become dynamic, and it will be the service itself that is exposing the interface. And then the execution of an action, of course, may lead to different state, because at a certain point my machine has to do something, maybe with a given probability will do something, and with another probability will do something different. Because basically, from outside, from the point of view of a controller, of an orchestrator, I can only observe the machines. I cannot do what they do internally. The basic principle of services is black boxing. So the service is a black box for us. So we can observe. And to have a valid observation, we have to model as different state of computing in in which you can read the machine. You can read. So I present the two basic models that will be used. On the one side, you have the simple model. Let's call the deterministic model, because in this way, what the model is that an action will lead to a unique state, and I assume that the execution is always correct. For example, I have a rotor builder machine. We'll see now a running example afterwards. So it's a ready. If someone will call the action build and retrieve rotor, it will move in the state down. Here I'm modeling that the machine cannot fail. If it fails, it means that the execution has not been performed. Or a more complex model, we'll see that we provide a solution in the first case or in the second case, in which I use a stochastic model. So the action leads to different states according to different probability. And the probability is a number that somehow represents in a combined way all the possible features. Or maybe it's something missing, or maybe it's a real error. Of course, when I need to do some abstraction if I want something that is computationally feasible. So in this case, I have ready. The build retrieve rotor with a 95% of probability will move in the status done, and I will have the piece built, or with the 0.5% of probability will go in the status broken. That means that the piece has not been completed or the machine stopped at a certain point. And we will see how it's possible to orchestrate these two cases, of course with different computational costs, and we will reason about it. So at the end,
will there be interaction with the business process behind?
It will be up at the level of orchestration, just
we will discuss
yes,
that. Thank you.
So that is what Frank is asking. So how I see at this point the production process? I see the production process as a composition of services. Here I use what was called the Roman model. The Roman model was an approach to service composition that many of you probably know. It was 20 years ago, it was very famous, probably still the most cited device, so I don't know. The idea of the Roman model is that I model something like automata, as we did in the previous, and I see the composition as a system of automata. So basically, I'm using automatic reasoning techniques like different types, let me say, of cross product. I'm able to simulate all the possible execution to choose the best one. Of course, from what I said, you already see which is the issue. The issue is that this may be really computationally expensive. And this is why we are moving to a more probabilistic approach recently, in order to overcome this limitation. So, the processes, the production processes, are basically an orchestration of services, so a kind of big automata that coordinates the single automata of the services, and we have different variables that can solve different issues. In particular, two of them. On the one side, what does it mean to have adaptiveness in this context? To adapt to some issue is a problem of replanning in the terms of a DIAG. So if something happens, this means that the original orchestration is not valid. I try to replan via the services in order to make them reach a new state that is the most similar as possible, and we will see a little bit what does it mean, the most similar as possible, to the original one. So it's like to say that you have a specified orchestration and you want to get back to that specified orchestration. The other approach is I can see the problem as a problem of synthesis from the formal method community, in which I try to build all the possible way of orchestrating. Of course, this is the double exponential. And when something happens, my job is just to take one solution out of the pre-computed one and to say, okay, for some reason to jump from this state to that state, now let's go on to that state.
Do you replan only for new orchestrations, or can you adapt existing orchestrations?
According to the two models, now I try to give an intuition. When I replan the current orchestration, trying to revert to the old state.
And you transfer the existing instance data?
Yes, exactly. I transfer the existing status, the context, let me say, to orchestrate. In this other approach, that we'll see there are different ways to solve the issue. This other approach is like before, at the moment -1, I computed all the possible orchestration that are possible with that service composition. When there is an error, I just pick where I am, I check in this big machine that is the cross product of all the possible execution, and I move on from that on. So there are two different approaches. Of course, we'll see, and this will be presented by Luciana and Flavia, that in some cases you have some properties, in other cases you have other properties. And in the conclusion I will tell that the future, in my opinion, of the research is to try to merge the two approaches. So far we are not succeeded, but maybe altogether we can be able to succeed. Because basically, what are the different that connects the different strategies that we can have to adapt? We try to give through an intuition. In our vision, you can have instance repair, what is called instance planning, and what is called policy based. And this is a typical way in which we classify possible way of solving the issue. I reported only our papers, but there are many papers from the community. Marco, for example, studies in the past similar approaches that we call instance repair. Marco with Alexander, it was a long time ago basically. Many other of you, I just mentioned them too, but without hurting anyone, make other example. What are the different approaches? In the instance repair, I like to say, you have a specific orchestration. At a certain point, the orchestration fails. Is what is presented as a dashed line. What you want to do with the replanning is to get back the execution to jump in the next stage that it was on the original plan. So it's like to say a local recovery action that allow you to go on. Why we call instance repair? Because in any instance it's like a story per se. So basically, I have an instance, I have an error, I correct the instance in order to get back on the next scheduled state, or the more nearby as possible. Then we have instance planning. Instance planning is a little different way of solving the issue. I have an orchestration. For some reason it failed. I don't want to force the system to get back to a state, because maybe it's no more possible to get back. There is no a rollback action or something like that. I extract the goal that the original orchestration was having in my mind, and then what I ask the system is that, don't forget about the orchestration, just let me back to a state, to the goal, the same goal that I wanted to achieve at the beginning, probably with a completely different orchestration.
But don't you run into problems about monitoring, so that human beings that monitor the process are confused because the process model has changed?
Why you say that the process monitor will confuse? I have a straight that check everything.
If I'm a manager and I'm used to observe my business processes,
yes.
a sudden a company is there, take a look at the referee representation, it has changed. I will be confused, isn't it?
No, our assumption, of course, is that in production process the orchestration are very well defined.
Sure.
Okay, so the instance repair is what typically in our experience is repair. In this way, it is right that you may say it's confusing, but there are some settings, especially not maybe on single production, but when we have value chain, so complex inter-organization, that may be some partners doesn't care how you achieve the product. Sure. They just care that you get the product. Yes, thanks. Sorry, Frank, you are right. So let's say that this is more useful when you are intra-fabric,
okay,
intra-factory.
Got it.
And this is good. Thanks, thanks.
Yep.
We need to be more clear. And then what we want to try is to have a policy-based orchestration, a policy-based repair that is a little bit more complex. So what we do is that we have a declarative specification of what we want to achieve as a goal. The system, and this is what we call the policy. What does it mean, a policy? Potential is not a single orchestration, but is a family of orchestration. All of them lead to the same final set of states that for some reason I define as equivalent. When something happens, I want to replan such that I stay in the same, let me call the intuition, area of policy that was originally scheduled. And this is useful when you start inserting probabilities, so you want to model a lot of issues. Again, this is probably more appropriate for large coalition, because in that case you don't want to have micromanagement like in the instance repair, but what you do is that you want to maintain the global policy of the value chain. Of course, I anticipate the first one, probably you can address with the planning, automated planning. The other two is where you need the synthesis techniques. Okay, this is...
Are you taking care of the issue itself as well? issue might propagate and disturb the whole thing, right?
The issue, yes, of course, the first case is applicable when, as you said, the issue doesn't propagate. So I just stop something, but for example, I have a recovery action or a substitute action. The other two take care of the issue, because when I want to achieve the same goal and I don't force the system to go back to the original orchestration, this is exactly for this reason, because maybe my issue in look ahead has created an issue that if I get back will represent. So I say, let's forget it, let's go to the same plan and we achieve the plan. So it's like to say that we completely change maybe the production. Okay, an example was during COVID. Abstractly, of course, in which the factory completely changed their goal, so they remanufactured everything in order to go there.
Yes, thank you. I have two questions for understanding. If I look at your figures, I have the feeling you are talking about continuous states and continuous time.
No, it's a discrete. I just give the intuition of a step. No, the good point. No, we are dealing with the single action.
The second question, we are talking about instances, how the notion of instance is related to the notion of case.
Instance and case for me are the same. So I call instance is an instance of an orchestration. For me, is the same as a business process case. So it's the single execution, is a trace, let's say, if you want to use the process mining terminology.
But particularly if you're in scenarios in Industry 4.0, the notion of what is a case is not that clear. You have different parts, you have an order.
Yeah, and this is why I think that it's important the model that you do of the orchestration. So you have, for example, a different part. Then the execution of a piece of a smart object as maybe is a case. So it's up to us as a modeler to give in the system the right notion of what is a case. And your question also made me clear that these types of modeling, my assumption is that it works very well with the discrete or batch production, not with continuous processes. So you cannot apply to the chemical world, for example. But if you are producing cars, so once the production of one single car, the orchestration of the production of the single cars is a case.
But you always assume the single case understanding.
Yes, no, you have the multi-case, but the multi-case, the system will treat them as single instances. So in my system, I can run a reason on the orchestration of case 1, a reason on the orchestration of case 2, a reason on the orchestration of case 3. So I'm focusing now on the solution techniques for a single case. Of course, they may happen only concurrently, and this is against why we put the probability in the model, because if the machine, for some reason, may fail due to the concurrence, I can just observe as a probability. Here, the machine learning I will present in a while can help, because the digital twin of the machine reason about it and give you a probability. Of course, if you want to have some computing, you have to abstract in some way. So that number is where you abstract the stuff, like the concurrency, for example. I'm not saying that this is the definitive model, of course. It's just a proposal to work on in a more, let's say, computer science way towards industrial process. So, how do you make all of these? As I said, the first is that in typical IIoT data, IIoT is industrial IoT, so it's basically the set of protocols and technology that allow you to build the system are very fine-grained, and typically they are not at the proper granularity if you want to use AI approaches, like for example, automated reasoning or planning. Because in that case, you know that continuous values are difficult, you cannot do computing over continuous values, so you have somehow to discretize. So, and in particular, IoT data are continuous, they are a good domain. So what is the idea? The idea is that the wrapper I will present in a while, the wrapper over the real machine is where the system, and there is all a bunch of research to do this, how to do this automatically, should be able to abstract such granularity mismatch in order that continuous value became standard, became discrete value. Allow me a very stupid example. If the issue that my machine can have is that the temperature goes over 40 degrees, This is an issue that we have in a company in which they are producing cardboard, and if the humidity is over a certain threshold and the temperature is high, the cardboard production should be stopped because the cartoon becomes too wet with the humidity and you cannot produce. But at the end, you don't care if it's 23, 24, 25. The threshold is 40. So what does it mean 40? That, okay, I have my sensor, that is what we have done there, that measures the real temperature and the real humidity. But what I can do, I can revert to two simple propositional values. One is temperature higher than 40, the other is temperature lower than 40, humidity higher than 25%, humidity lower than 25%, and the software, the firmware that is inside, just what it does is that it reads this value, but send via an API to our controller just the value A or B, C or D. I don't have any more continuous value, I just have 4 values. And 4 values are manageable in our context because the combination that you can have during the reasoning phase is manageable. This is an example of what I call data abstraction. The issue is that currently you have to do by hand. In my opinion, a lot of research is how can we use, for example, machine learning in order that this abstraction layer in software is done automatically during runtime. So that to create a kind of general purpose middleware that can do the data abstraction for the AI at the lower level, at the higher level, such that the system works in a computational effective way. This is a challenge, in my opinion, as to be addressed. So what we have is that we call this the physical to digital interface that is easily where you have to modify. We have, for example, some example of web tool. I have a location. Now is an example was for a smart application. I care about position. What I can do is that via a web tool, I can just derive that this is location 1, location 2, location 3. In this way, I have a bunch of continuous data. I can revert to a set of finite domain data. They are in programming terms like that I define a new type. And this enum type on finite set of value is what I use at the level of the reasoning. That makes me the stuff computational expensive. The same is in a fabric. In a fabric, they have the concept of shop floor. So basically, that position, they don't care exactly if the big machine is there or 20 centimeters before. This will be resolved by the low-level controller of the robot. At the end, what you want to know is the robot is in position A or position B. And you can abstract a bunch of many continuous value in a single, let me call, propositional value. Propositional in terms of logic. Another example that we have is that we made an Arduino board that was able to do again through a web interface. You can define what are the data points that are interesting for your computational domain, and then it creates the software, makes the abstraction. So continuously read the value and send back the propositional value up to the system. So the architecture in which we have the service machines as a service, in our opinion, is the following one. I have the physical device. In the real fabric, what they do is that all of this works with OPC-UA, the most of them. That is the de facto standard, is the general purpose middleware in factories in order to have business. What I have is that on one side, I have what I call the abstraction of data values, the digital to physical interface, that performs sensing and knows how to expose the value that are read via an industrial app interface. Industrial app means completely REST API, so they are really web services as we mean them. On the other side, when some commands will be received by the industrial app interface, we have the actuation. And again, the interface, the digital to physical, should know that the command that is abstract should be reverted to a low-level command. So how to devise this stuff? Now we do manually. Manually means through programming, special case programming. In my opinion, this is interesting to investigate this. How to have systems that can semi-automatically create such a layer. Because this will make really scalable the idea of having service inside factories. You want that is created, so the abstraction should not be done every case by a programmer. Just a minute, William. And then you have another field, another area that is the machine learning toolbox, in my opinion, that continuously read the data, and what it does, produce predictions over fault, over possible errors that may happen, and again, those faults are those ones that are exposed as probability, for example, in the industrial lab interface. Our idea is that probably at a certain points we'll discover that the machine learning toolbox can be used also in the abstraction layer. Please.
So I have a couple of questions. So one of them is I was recently in Stuttgart design for a factory. When I see this factory, there's a lot of human machine interaction. So do you also, does your model also, let's say, apply to those situations where you're human as a service?
Yes, I mean, okay. So the first, assume that this is a completely autonomous robot, and here there is an operator that does something complementary to the robot. In this case, I will see as two services. One service is the robot, the other service is the human, that probably will have some wearables or a tablet or whatever. Easy will have as well easy interface industrial API, and is the orchestrator that makes them communicate. If conversely, your device is a cobot, for example, so those type of robot in which you have a man that drives the robot, for example, there are some types of arms in which is the man, is the union of the man and the cobot that are the service. So again, here is where you have to model at the proper abstraction layer. It depends. If the operation, this is my point of view, is done solely by the robot, is the robot that is a first-class service. If it's the human plus robot, is the agglomerate that we model as a service, with its own interface, probability to fail, and so on. I don't know if this answers your...
Roughly, and also how do you deal with complexity? So suppose you would apply this and you would have thousands of it.
And we have...
How do we take care of people consistencies?
Sorry, Luciana, I didn't get that. We have thousands of...
Now, thousands of these physical devices at the shop floor, right, with humans. And
Yeah.
they're all interacting. So how do you deal with this complexity? How do you deal with potential conflicts, for example?
Yes. Again, in my view, is a problem of issue. Many often I have thousands of devices, but many often they are sensors or actuators that does very simple operation, and then you see the entire machine as the entire equipment or station as the service. So the approach that I have is modular. So you have aggregation at first level orchestration, then you have another level orchestration, and then you have another level orchestration. Because at the end, we know computational methods, if we go over thousands, are not manageable in such a deterministic way. So, based on our sensor, we are measuring temperature, blah, 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 but this is not the single sensor that is exposed as a service. The service is what we call the cardboard digital twin, in which in that case is able to say, okay, start production and production, give me the number of cardboard that has been produced and so on. Then the implementation inside hides the production, the monitoring of the different values and so on.
So as also all the intelligence, let's say, is in the composition between the manager, not in the machine's device.
Yes, exactly. All the high-level intelligence is in the orchestration. I will show you why. And then in the single pieces, it's like that you are decreasing intelligence, moving more or less to simple data exchange among values. Good point to say. Thanks. So just before the break, we are perfectly in line. I want just to open a small intermezzo. Intermezzo is when in music you have some piece of music that depart apart from the main discourse. That is speculating over smart system and closed loop approaches, because I found it very interesting. What is a smart system? Because at the end, the Industry 4.0 is what is called the brand system. The definition is not mine. It's from Brand Savage, that, as you know, is a very famous researcher in software engineering, that recently was very interesting. He gave a talk to Kaise, and he defines a system, a smart system, as a system that sends the states of its context and that changes in the context in order to change its internal states as they occur. And notice we have so far we have spoken about exactly about this. Then it's a response to some changes in a timely manner, that in a way is a consistent to the intended purpose, substitute purpose with the goals and the consistency with having a formal proof that the system computes in the right way, and we are back to what we are saying, and adjust its behavior to deal with previously unknown or unexpected situation when there are available data all based. So somehow I think that Industry 4.0 is exactly what Brown calls a smart system. And, sorry, too much. And these systems are complex. According to Brown, we have not yet a solution. Why they are complex? Because when we get into the details, you have issue of concurrency, complexity, unpredictability, why we need to insert stochastic approach to automated reasoning, because basically, otherwise you cannot model the unpredictability. There are idiosyncrasy, physical constraints, mutability. So the idea is that in this type of system, according to Brand, but I made myself this vision, it's useless to try to design in advance a system that is correct by design situation. It's too complex. According to him, it's better to have a reactive approach. I build a system and I make the system adaptive. This means that I try to react when something happens. There is no point, according to him, due to the complexity of current system, to design from scratch, as typically we do in a in a traditional engineering approach. All of us, when we teach our students, we say, okay, you have to build the system robust since the design phase. So the approach of Brown is that, no, do the system according to the happy path. So what can be correct, and then equip the systems with adaptivity by design, with some general methods that when something goes wrong, adapt themselves. And this is why we are trying to show you. So we can use AI to try to adapt when something goes wrong at the instance level or all the classification that we have done. Because this is the only way in which we can be fast in producing the software as it happened, as we are required today, and at the same time guarantees the minimum of robustness that you may have. And now you can do this. We have to revert to old style control theory, basically, that I say old style to joke, of course, that is to have a closed group approach. So I model the system as a function that takes input and output, and this is what we are trying to do with our model. And then you have the input. When you have an output, what you do is that you realize that your output is departing from the happy path, what we saw before with the intuitive figure. What you do is that you have some control system, the controller, what we call the orchestrator, that what it does, it produces a new input and tries to revert the system to change to the original state. Basically, this is what in control theory they do since a long time. They have done so far mainly in the continuous world. What we are doing with using AI, this is the idea that we have, is that you can try to do in a computer science, basically. So let me call the control loop approaches for computer scientists. So you have a system, you try to take the output and you work this. Notice that there are some framework like make, monitor, analyze, plan, and execute, in which you are easily basically based on this idea. And this is what is, let's say, the intermezzo, so the research that somehow gives the context of the research that we are trying to do.
Is that wrong?
Is that?
Is that wrong, that approach, or has it some flaws? Is this approach wrong? Because this is a predictive approach, right?
No, it is a reactive approach.
No, but if you analyze, you can predict eventually from the past, you know, you're extrapolating.
You can, okay, yes. The analysis, I say, I talk, is when you start to put in some level inside. In the previous slide, the meaning of analyze here is monitor is get the data. Analyze is understand. It's not analyzing in the meaning of prediction. It's analyzing the meaning, check if the situation that you are sensing from the world is the situation that you are expected in a kind of virtual idea or idealized world. This is analyzed. At that point you plan how to get back to the earth and execute it.
But that's one definition.
Massimo, I worked on wave loops in DB2.
Yeah.
Did.
I know. In fact, so
did.
databases were done
Okay.
30 years ago in this way. What we are trying to do is that single pieces of software well done exactly with this philosophy. But if we look now at the current, at least this is my personal view, of course, I'm ready to be attacked. If you look at the current situation in processes, services, let's say that is still not the mainstream. I think that you can agree on this.
Absolutely.
But somehow the thesis that I'm trying is that let's do as well. Of course there will be new issue because we are really at a higher level, a lot of stuff to conclude, but this is the way to address it. Is that single pieces of good software were done in this way. Somehow we as a community, we forgot about it. I think that you can say, you can agree on this. So it's time probably to get back. And I'm happy that you agree on this. It's very important for me.
That's the question.
Oh, sorry.
Sometimes the situation is even worse because the change of the system may not be a mistake, but done on purpose by an engineer just fixing something.
Yes.
And how would you differentiate?
In the current modeling that we have, we don't differentiate. We'll see as a broken state. Okay. Of course, the philosophy that I have in mind, but it's just a vision. In this way, yes, in fact, I try to get back to the original goal, and then, and this is the innovation, you can start putting some machine learning. This talk was not on machine learning, but I'm trying to see where in the philosophy machine learning can help. To which, for example, you can mind why in that situation the things was broken, that it was not scheduled, so you can use techniques like data mining or what they call or causal relation analysis and so on. Try to understand so that you tell to the orchestrator, look at the next execution, when it will be this, now you have an exact probability when it will happen. It's complex, I know, but if we don't try, we'll never solve the issue. Do you agree with me on this? So it's okay. So this was where we had to go, that in this control theory-based approach, like we call closed loop, we have at a certain point to introduce some ML, but not with the idea that ML is at the orchestration layer. I don't believe in that, because in production, we want that the orchestration is safe, should be provable that is correct and so on. But in the phases in which you can produce the probabilistic stochastic part, this is where I see the ML. Of course, again, this is a personal opinion, let me say, and we can start. Said that, we have another news. What is so the global vision that we are working on, and after the break, then we start giving the details of the single solution that we have found so far without any willingness to be exhaustive. So basically we see whatever is modeled as a service. The service has typically two types of API. One is what we call the synchronous interface. So it's a REST service in which you can ask for data or executing something. And there is a query interface. We call query that is when you just want to read the data. So the difference is that the sync API has a side effect on the machine or the operator on the actor. In general, the synchronous interface, the query interface is just read-only when you want to get data. And from the implementation point of view, this is a difference because you can do this much more fast than this. It's more reactive, so it's a problem of engineering the software. Then there will be two interfaces that we don't have currently in our systems. That is the simulation interface. Let me say the one that will say in the future the probability that something can face. Currently in the running example that you will see, this probability are fixed now. In the future we want that this interface will tell, so that the planner in the future can say, how is the probability that if I do this in 3 steps you will reach that state? And with machine learning I believe that you can say. And there will be probably also an asynchronous interface for streaming data, because something that I'm not dealing, I admit it, but is the issue that some types of production wants streaming data. For example, what you were mentioning about continuous processes, like chemical processes and so on. In that case, if you don't have discrete steps of execution, you need to have continuous data. This is not done, honestly. Not. Then what you have a controller. The controller is driven by, let me call a supervisor, would be the production manager, that set the goals, push the button, let me joke in this way. He has the plan for the production, he can continuously monitor what is happening, and he can choose how to drive all the system. This is a kind of the reference framework that we want to work on. And as we said, when there is an error, new solutions are proposed at runtime. So we have designed the orchestration in the happy path, and we are reactive in order to work with this. Just technically, we have prototypes of a target description language, so it's a JSON-based language in which you can express the targets of the goal in order to execute it. This is just a sample. Flavia will show in the demo, but just to know that is a concrete. So we have a kind of, let me call it declarative language, JSONized. Let me say it this way, because we are in the era of JSON. If I would have given this talk 20 years ago, it would be Wisdom. But Wisdom now is old-fashioned. Then you have a service description language, that is what is exposed by the wrappers, basically, in which the basic feature is that you have to describe attributes and features. Attributes are those ones that model types and statics immutable values. For example, the definition of the actions. In object orientation, we call it the types. And the serial number of the device. Notice that if you have something that should be initialized, you will define attributes. Like when in programming, you have to define a variable and to have an initial state immediately since the beginning. Features are those ones that are used to model dynamic values. This derives from the fact that the logic behind, that we can see in the paper, is based on situation calculus in many cases. So you need to define fluence, so something that changes over time. Just for those of you that are interested, fluence over propositional value. This is the need of other abstraction. Otherwise, you are not able to deal with anything. And these are examples of our specification, basically. And now we have the break, if you are happy, and after they will start showing the technical approaches. Until 15, right? Yeah.
Immaginatevi la valorizzazione pubblica per la device, non veramente sì. No, perché devono fare una foto, ho detto chissà perché. Dobbiamo armare.
Vuoi vedere la lezione di
Dai, ci siamo. Scusa, voi c'avete a destra un capito? Raga, fate 15 e 30. Raga, fate 10 e 10. Scusa, voi siete Francesco ha preciso, fate 15 e 15. Ah, sì, devo fare Francesco.
Devo leggere i
Vedi quanto fa Francesco? Francesco va giusto, ma c'è 15.
E video perché non riuscivo a capire.
No, ragazzi. Perché?
La prima volta che vedo la conoscenza.
Ma è che si sono funzionati
Non è ingegnere.
Stava questa sessione di questa questa mi ha fatto un paio di domande e sappiamo facevo 5 chi si è laureato
però lo psicologico
davanti alla
Poi si ricordo bene che mi serci per ripetere la
io nel secondo fascio
no, scusa, la storia che c'è laureato è stato causa insieme a
No, c'è Leo,
non avevo più
questo ha problemi con la stessa si parlava nessuno mi aveva detto che non si aveva detto io sono arrivato con un papiro perché sei arrivato l'anno scorso e nessuno ha detto a un certo punto erano stati 15 minuti che stavano prendendo soluzione.
Quindi a un certo punto il capo della commissione ha iniziato a fare. Non c'era, ma non era il capo. No, era. Però comunque ha detto dai, poi ho fatto il gesto. Adesso la nota si è un po' incazzata, però l'ha usato quello che si può dire. Si è andato. Ma l'ha fatto ecco, cazzo, mi sto così.
Diciamo che già questa non è
l'hanno fatto la gara, non so perché non so il voto di partita, no, non è non so più di partenza, non so quanti punti ha preso, però comunque io sono andato. La madre piange, è uscita fuori, tutti a guardare fuori, c'erano quelli che provavano a presentare dopo, stavano a guardare fuori. Anche i professori. E poi quando l'hanno fatto entrare gli hanno fatto che sono davanti a tutti, davanti alla commissione. Per la Tiziana che era solo fare questa ieri proprio veramente il principino, perché
solo di fuori
lo svantaggio suo del concorrente se volessero iniziare
un attimo, questo qui è il Cilo,
non c'è farmi invitare a casa perché se mai dovessi andare prima di andare devo lei già è iniziato a fare
della macchina
nei dipartimenti io ho detto no, trasferisci dai
Volete un po' di approfondimento? Ormai è così.
l'ho avvocato con
no, la prima parte sì, poi iniziamo questi aggiornamenti, la seconda è rimasto.
Quindi hanno fatto due strade diverse.
non c'era foto
È meglio così,
sorry, in H. 5 minutes, sei arrivata. Mi ha lasciato da vicino, da vicino. Poi mi è venuta vicino, dopo 10 minuti, ma Calimera che poi...
Calimera che poi
coraggino.
Mi ha lasciato da 10 minuti.
supporta quelli
Sì, e vediamo che stanno tipo...
diciamo
sono capissimi.
sono due dritte no non c'era lei sta così se pensa a posizione di sta fare l'imitazione del fenomeno ma che più c'è
No, anche se
c'è il maglione
e finita il fianco che sta no questo